you can set a watch point there and grab it there instead of having to follow it all the way through the decompression or the decryption. So the other thing it'll do is let you, like I said, start the trace in the middle of the program, and you don't have to take a trace of the entire execution because you might not want all the stuff in the beginning, all the setup from the OS. So okay, the current state is that I don't implement the simulation part that I was talking about that Microsoft had created. I do the caching on the side where you're following the program. So as the program's running, you keep track of the registers, and if a register hasn't changed in between two executions, you don't spit it out, which is really dumb optimization, but you have to do it anyway. And multiple threads are not recorded. They're recorded in separate logs, but there's no sequencing. So there's no way to put them back together right now. I've looked into it a little bit, and that Nirvana paper actually describes how to go about it. So let's look at something. We'll start the demo now. So here's a program we might want to trace. Okay, this is just test 001, and it takes some input on the command line and passes it to a function, and then checks the first 2 bytes of the first argument on the command line. So if the first one is an A, it'll just print 1. And if it's not, then it checks the second one. And if the second character is a B, it'll print 2. Otherwise, it'll print 3. It's a really simple program, just to give an overview of how the tool works. So I think it's already compiled, but I'll make sure. All right. So what we want to do is we want to run this trace capture tool in this. And we're just going to give it AA on the command line, so it falls into this first area right here. But before that, like I said, we have to set those watch points. So what we want to do is we want to mark this. So we want to put a watch point on F and mark A and B as tainted, because that's what we want to follow through the program. So to do that, we're going to open up IDA, which should already be open. Oh. Pretend you don't see that. Okay, there's the test 001 IDB. And we'll go to main here. F, where's main? I'm on a netbook, and I'm not doing so great on it. Okay, here's main. So 2 things we have to capture. One is where we want to start the trace. So we're going to capture this, the address of main, because we'll start capturing at main for this. That's the offset is 41. So where's the Okay. Here's the execution of the voidness trace tool. So we have to execute it through pin, because pin is the DBI that voidness runs under. And we pass it voidness as the tool. And then we say the start module, where we want to start tracing, is this test001.exe. And then the start offset is 11460, which we see here. This was loaded at 400000. And then we pass in the watch point file, which is here. And that specifies where we want to start the taint. So then we have to go into F, because that's where we want to start the taint. Here it is. So here we go. Here's F, and we know that this is the address, and that's what this is here. The second line in the file is the address. The third line is an expression that tells you the address of the taint, and that's going to be the ESP plus 4, because we're starting here before we push on the EBP. And that's going to be A. To get A and B, we make the size of it 8 instead of 4. So here's 8. So that's how we set up our file to run the tool. And here's trace test.bat, which we're going to run now. The startup of a dynamic binary instrumentation tool is actually kind of slow because it has to cache all the things that are going to get. The startup of a tool, of a program, I mean, executes a lot of code only once. So you're going to have to go through that instrumentation step many times, and you're not going to reuse any of the instrumentation things that you've done. So DBI always takes a minute to start up, no matter how small the actual tool. So we're done that, and let's see. Well, I'll show you what we got out of that trace tool. So what did Voidness produce? Here is a ASCII version of what it produced. Okay, so the image loads up top. It's going to be the standard things you see: kernel DLL, and then the exe and NTDL, and then it'll say thread start, and then a bunch of system calls. And then image loads, another thing we record. And then things like the instruction address, and then registers that are, and the value of the registers that have been written or read. So that's, a giant file full of that. And it's not stored like this, but this is just a dump of what it, actually means. It's stored in a very compressed binary format. Okay. Now onto the static analysis. So now we have this trace, and we can't really use the trace yet because we have to do that analysis I was talking about first, which is the control dependence analysis. And what that takes is, and before we can do that, we were going to use IDA to just grab the control flow graphs. So we use an IDC script to grab the control flow graphs and spit those out into a really easy to parse ASCII format. I'm not going to go through that. That's pretty simple. A lot of tools do it. After we have the control flow graphs, we're going to do this control dependency thing that I was talking about. And that's going to spit it back into this analysis DB, so we don't have to compute it every time. So if we're working on the same binary a lot, we'll just do it once, spit it to the database, and then reuse it again. And this is what a lot of the static analysis tools do, like all this dynamic stuff, and PageRAM stuff does it too. So let's talk about control dependence. And to talk about control dependence, the way you calculate it is through something called post dominance. And the way you calculate post dominance is by reversing a control flow graph and calculating dominance. So the dominance relation is if X appears on every path from entry to Y, then X dominates Y. It sounds more complex than it is, I think. So, for example, 1 is going to dominate everything in this graph because you have to go through node 1 to get to anything else, right? What about, which nodes dominate 6? Well, 2, 1, and entry, right? 3 and 4 don't dominate 6 because you don't have to go through either one of them to get to 6. Does that make sense? Yeah? Okay. So 1 and 2, and 6 also dominates itself, but we're not gonna care about that. What about 8? Well, the only node that dominates 8 is 1 because everything else is conditional on the branch that 1 takes. So just 1 and 8. Post dominance is calculated, like I said, as the dominance on the reverse control flow graph. And then control dependence is calculated based on that. X is control dependent on Y if Y determines if X executes. It's pretty simple though, right? So, anything in the middle of this graph, so 3 and 4 are controlled, 3 and 4 are control dependent on 2. 2 is the branch that you take that determines whether or not 3 or 4 execute. It's just the one right above on the tree, the nearest sort of branch point. This control dependence is used to be able to match up the taint that you calculate to the instructions that are sort of dependent upon that value. And that's another type of marking that we'll put on our IDA plugin. Taint propagation. So actually, let's do the control flow control dependence execution here. The demo. Okay. Oh yeah. It's already in the database. So we have that done. Now the taint propagation that I keep talking about takes the execution trace and the control dependence relations that we saw, and walks over the entire trace and calculates the flow of the data and writes out this taint info. So here's a sample. If we put a watch point on the call to read U32, such that EAX was marked as tainted after this call returned, then we'd start by, so after the call, EAX would be marked as tainted. Then the add EAX and 0x20 would execute, and still EAX would be tainted because it goes back into EAX. Then there's the load effective of EAX and 4 times EAX, and once again, only EAX remains tainted. We push EAX and we mark that address on the top of the stack as tainted. Then we would, after the XOR EAX, which is going to clear EAX, we'd clear the taint value on the register X, but the taint would remain on the stack address. Then we push this 0 value. Nothing would happen because EAX taint was cleared, and then we'd call function. If function was something we were interested in, we'd see that the first value on the stack was tainted, and we'd follow it through that function. Now, once the taint info is computed, linking the byte offsets from the tainted input to logical chunks is next. This is, let me show you the plugin. It'll be a lot easier to understand, I think. So on the right side, we have this syntax tree, and it's really weak for this example. We only have these 2 values, A and B, and they have no relation to them. But if we click on node A, and then I got to refresh this. There we go. And we can do the graph view. So we can see that A here is, here's the value of A on the stack. And we see it's transferred to EAX. EAX takes goes into another place, a local on the stack. And then the control, the taint gets propagated down this way. And I'll show you how it was calculated over here. Here's the output of that taint analysis tool. Well, the debugging output. Here's where the taint starts. Here's where those watch points I was talking about occur. The ones that we set up on F. When F is entered, we taint 8 bytes here. And so it's A and B on the stack.